So I have made a video for the first part. So here this video is about part 2 of the Nusswinner model. So we talk about how to optimize the order quantity in order to maximize the expected profit, which is also the classic Nusswinner model we have introduced in the bachelor course. So here is the continue the HAMR 3.2 example. So we also know the cost and price information for this example. So the selling price is $190 and the purchase cost is $110 per unit per suit. And if you cannot sell this item in the regular selling season and you have to sell them in the discounted market, then you have a salvage value is $90. And then O'Neill, this company, has a too much or too little problem. So if you order too much, inventory is left over at the end of selling season, and then will cause a salvage value. And then if you order too little and the sales are lost, so this is a lost sales problem. Then here recall our demand model is a normal distribution with mean. So we have a normal distribution of your demand with a mean 3092 and standard deviation. And then now we talk about how should we determine the order quantity for the forthcoming selling season in order to maximize the profits. We do not go through the traditional mathematical derivation process, so we directly present to you the result, or we call it a solution in this lecture. So given the economic information for this example, then we can actually work out two new values. One is called C0 or CO, this overage cost. So there are definition about the overage cost, and also there is a example about HAMR 3.2, how should we calculate this overage cost. So first let's see the overage cost is a consequence of ordering one more unit than what you should have ordered if you had know the demand. So suppose you had leftover inventory, so CO is the increase in profits you would have enjoyed if you have ordered one fewer unit. So I normally do not like this statement. It's really a language game. So let's try the example. So for the HAMR 3.2, so the cost is $110 and the salvage cost is $90. This situation only happens if you have leftover inventory. At the end of the selling season. Then this cost called overage cost, and then at the end of selling season you have paid the purchase cost $110, but now you can only sell this product for $90. You basically make a loss. So if you have not ordered this extra unit, you actually save this 20 extra loss. So that means you can enjoy the more profit. So on the contrary, we have the underage costs. So underage cost is the consequences of ordering one fewer unit than what you should have. So if you already know the demand beforehand, you can actually order the optimal quantity, just match the supply and the demand. But in this case, we talk about you actually ordered one unit less. Then what's going to happen? So that means you actually have a lost sales, and then the loss you actually made is the price minus cost. So in other words, if you have ordered one more unit, you will achieve a profit of $80 for this unit. So that's an underage cost. Based on this underage cost and overage cost, we actually can find the optimal order quantity. So if you understand the meaning of overage cost and underage cost, now we can put them into the real sales situation. So now, for example, you order the Q's unit. So and then the cost situation will be if your real demand is less than, should be less than, we do not consider equals. So your demand less than Q units, then you actually need to pay the overage cost. So that means this Q's unit will be in the leftover inventory. And then if this demand is greater than Q, you actually risk to have an underage cost. So that means you have a lost sales. Given the stochastic demand, we never know when what is the real demand. So we have to consider the possibility of this overage or underage cost in your overage and underage probability when you actually evaluate the profit. In that sense, we continue to actually think about how to balance or how to make a trade-off between the underage cost and overage cost. Of course, the best is to actually have a equal. So you have a underage cost. Equals to overage cost. Then basically you have actually no penalty in your problem. So you make a decision, demand equals to your order quantity, then maximize your profits. So in this graph, we tried to actually plot the expected underage costs and then the expected overage cost. So this is inventory cost, so this is actually salvage cost if you think about this way. And then we can see when you order more and more units, you actually have a higher and higher probability have a leftover inventory. And then of course if you order less units, you will have actually you have actually higher lost sales. So when you move to the left hand side, you have actually higher lost sales. When your order quantity moves to right hand side, you have a higher leftover cost. So when you try to maximize a profit for your news window problem, so optimal solution actually is here. You actually consider to balance the underage cost and overage cost. This is actually the max profit solution. Then we can continue to to see how can we actually find the optimal order quantity based on this relationship. So now you can see to maximize the expected profit, we need to consider this overage cost equals to underage cost. So the FQ we have mentioned previously is a probability of the demand less than or equals to Q. Then the 1 minus FQ actually is the probability demand greater than Q. So that's actually how we evaluate or solve this problem in order to find the optimal Q. So in this equation, this optimal condition, so this actually called this condition called the optimal condition to maximize the profits. So if we rearrange this equation, then we actually get the optimal solution from the FQ. So if we have a explicitly defined probability distribution function, for example, D demand is a normal distribution, you actually can find the optimal Q is from the inverse function, inverse normal function. And then here we need to use a critical ratio. So this value of this ratio between the underage cost and the total cost is called a critical ratio. If you can find a critical ratio for your problem, that means you can continue to find the optimal order quantity equals to F inverse normal function of 0.8. So here the critical ratio is actually a probability. So later we will explain what the probability refers to. But here we just know this 0.8 is a probability. In order to find optimal order quantity to maximize the profit, then we need to call a inverse normal distributions function with a critical value of critical ratio of 0.8. So this can be directly solved in Excel if you know F is a normal distribution. So this actually equals to a normal inverse distribution with a critical value, and you need to know mu and standard deviation. That's how you find the optimal solution for order quantity. But in the textbook, they actually, in order to introduce the concept of lost sales and leftover inventories, they used the standard normal distribution function. So here we just explain how does it work. So if you have a standard normal distribution table, and then you try to find a value 0.8, so here 0.8 basically is between these two values, and then the 0.7995 corresponding to a value of 0.84, and then 0.8023 corresponding to a z value of 0.85. So from this table you can find zeta equals to 0.85. If this is optimal zeta value, that's how you find it. So you may ask me, why don't we take 0.84? Because this is based on the round-up rule in Nussweiler model. So you always consider the value will give you the higher order quantity. So here we choose the zeta equals to 0.85. So we know zeta is a standard normal distribution with 0 and 1 parameters. So we need to actually transform this zeta into Q star equals to mu plus zeta star times sigma. So if you do this transformation, you basically get the same Q from this F function. So next slides will explain how does this work or calculated. So if we continue with the value of 0.85 for your critical value for order quantity, then we convert this Z statistic into your order quantity. In the Harmor 3.2 example, then now the optimal order quantity for next season will be 4,196 units. So now we actually solved the Nussweiler problem, but here actually you should know this order quantity is based on the objective of maximize the profit. So it's not actually very difficult to solve a news window problem, especially to maximize the profit. But in practice, it's not always the case. You need to maximize the profit. For many retailers, it's more important you actually need to guarantee a service level. So for example, in-stock probability or fill rate of your products to your customer. So here we try to clarify different performance measures regarding news window models. Here we're going to talk about in-stock probability, stock out probability, and then expected lost sales, expected leftover inventory, expected profit. You will see that's actually a lot of values, but in the end they actually all correlated. So if you can find the in-stock probability, then you can find all the other values. If you can find the stock out probability, then you can also find the rest. So that's actually not a standard separate calculations. You just need to understand the relationships between different performance measures. So the first performance measure is the in-stock probability. So the definition for the in-stock probability is the probability all demands is satisfied. So assume you know the demand distribution and you would like to satisfy in what level you can satisfy all the demands. So that's overall performance measures. And then now we can see one example. So all demand is satisfied if demand is order quantity Q or smaller. So basically we're talking about if your demand, so the probability of your demand is less than or equals to Q, then all the demand will be satisfied. But the problem is this probability may not be 1, so you always get a possibility to satisfy all the demands. So the question is if Q equals to 3000, then to satisfy all demand must be 3000 or fewer, or we say lower. Then we just use FQ to do calculation. Then the FQ is called in-stock probability. And here we have actually a wrong formula. So FQ should equals to phi zeta. Phi zeta is related to the standard normal distribution, and F is related to the normal distribution with mu and sigma. And here is 0 or 1. Now let's try to evaluate the in-stock probability. Now the question is what is in-stock probability if the order quantity is 3000 units? And then the steps is actually first you can try in Excel. Here in Excel you actually can directly find the distribution values. If you know the normal distribution values parameters for your demand, you can actually also do FQ. FQ in Excel is a normal distribution with the 3000 units with a mu 192 and the standard deviation and 1. So that's how you find the in-stock probability directly. In the textbook, they also go through the zeta statistics. So if you find a critical value regarding your Q, then you actually can also use phi zeta in the standard normal distribution function or Excel. Then we have another function to use, but this value should be same. So it's not important how do you find these values. It's make more things you understand the meaning of the in-stock probability. So we introduce this in-stock probability. That's also because in the reality, you may need to actually make a decision about the order quantity based on a targeted in-stock probability. Suppose we wish to find the order quantity for the HAMR 3.2 that minimize leftover inventory while generating at least 99% in-stock probability. So if I just do calculation, then you know now you need to find a Q to make sure a in-stock probability of 99%. Then straightforward, you can find this Q value regarding this in-stock level by an inverse of this function with a probability 99%. So this can be called in the Excel by normal inverse function with a 99% and with your mu 392 and 1181. So that's actually is the simplest process you can go through. If you think that's too abstract, then you can also go through the data statistics calculation. This slide goes through a more complicated calculations. So 2 steps. First, you need to find a data statistic that yields the targeted in-stock probability. The good thing to use a Z statistic because any distributions can actually use exactly the same calculation for zeta statistic. So here, if you choose zeta equals to 2.33, then you actually satisfy your in-stock probability constraint 99.01. So you find the zeta value, then you transform the zeta value into a Q value or order quantity. So this zeta value, the calculation method for any problems will be the same. You find the in-stock probability and you go to the function table, then you find a Z value. After you find this Z value, you transfer this Z value into a Q value. So, but if you want to do a direct calculation, you should always remember this distribution actually related to the specific parameters. If you remember what is a profit maximizing order quantity, so which is 4,196 units. Now, in order to reach the 99% of in-stock probability, now you can see you need to order 5,944 units. Now the question is, would you really like to order so many units? And then what is the expected leftover? And then that's important for you to make a final decision. So after you calculate the in-stock probability, then straightforward you can find a stock out probability, which is 1 minus in-stock probability, so equals to then another value. Furthermore, you can see we also have a fill rate performance measures. So fill rate is different from in-stock probability. So fill rate is a fraction of the demand that can purchase a unit. So that actually shows if you're talking about individual customer, and this fill rate is a probability this customer can find the unit in the store. So the fill rate is also the probability a randomly chosen customer. So a randomly chosen customer can purchase a unit. So the calculation is fill rate is a ratio between the expected sales and the expected demand. So the fill rate is not the same as an in-stock probability. we have an example. If 99% of demand is satisfied, so the fill rate, then the probability all demand is satisfied need not to be 99%. So we can do a calculation here. If O'Neill orders 3,500 units product, the expected sales is 2,858. Then your fill rate is about 89.53%, and your in-stock probability actually is only 60.28%. So that they are quite different values. So it's up to you would like to use a fill rate or in-stock probability to make decisions. So this slides talk about how to calculate expected lost sales. The process is rather complicated. So if you can actually enumerate all the possible demand scenarios, then you can actually calculate individual loss values regarding different order quantities. So in that things, regarding different demand scenarios, so in these things you can just add all these different possibility, different scenarios together to calculate expected lost sales. This graph just show the intuitive explanations about the expected sales, but we do have an integrated result for this. This figure plots the expected sales regarding to the different order quantities. So the general information you can discover is the more you ordered, actually you have a less lost sales. So for example, if you order nothing, you actually lost basically entire market. And if you order 5,000, you have a very small chance to actually have a lost sales. So the lost sales actually approaches to zero when your order quantity is greater than 5,000. Then the question is, given an order quantity, for example 3,000, how much 3,2, and how many sales would be lost on average. So the calculation includes 3 steps. First, again, you need to find the zeta value, zeta statistic for regarding your order quantity 3,000 units. So you're actually now located in this probability, this normal distribution, basically the negative values. So you're somewhere here, and then so this is the zeta statistics you found. And look up in the standard normal loss function table, the expected lost sales with that zeta statistic is a function called capital L. So the capital L zeta is a customized function. So this can be derived mathematically. There is a formulation here. I actually wrote is equals to phi zeta minus zeta times 1 minus phi zeta. But it's not necessary you need to know this function. So in the Nusswender model calculator, you can directly call this value. Otherwise, you can always find this result from your loss function table, both in Excel or in the textbook. And then in the Nusswender calculator, you can just put the zeta value, and then you find the lost sales for this level order quantity. And then the expected lost sales is the standard deviation of your demand times the lost sales level, and then you find the lost sales of 572 units. So that's how you find the lost sales. The difficult part is how to calculate capital L zeta. We call it a normal loss function. So it's not necessary you know about that. So follows to the expected lost sales calculation Furthermore, we can calculate expected sales and expected leftover inventory. The purpose to introduce them here is to tell you, you can always open your book, try to find the formulas, then you find the method to calculate all these statistics for your inventory decisions. And at the same time, you can calculate expected profits. And all this relationship actually hold for any demand distributions. We talked about how to calculate the expected lost sales. That's also possible to calculate expected leftover inventory. So I have this question for you. Suppose O'Neill orders 5,000 Hammer 32, then ask you how many sales would be left over in the inventory on average. Actually, it's not sales, it's how many units of the products, how many orders. So we just change this into how many units will be left over in inventory at the end of the selling season on average. Similar with the calculation for the expected lost sales, we also need to go through 3 steps. So the most difficult part is here. You should know it's possible we can find a standard normal inventory function table. So in this case, you have to calculate zeta statistic. So if we do not calculate statistic of zeta, then we cannot find the leftover rate. Then we cannot actually estimate expected leftover inventory for your general distribution. But this, if you are interested on this leftover inventory calculation function, you actually we call it a standard normal inventory function. You can write them as a phi zeta plus zeta times capital Phi zeta. So that's how you actually calculate expected leftover inventories. So it's not necessary you know these formulas. In the news vendor calculator, you can directly calculate this leftover rate for your problem given the critical value of zeta. And then in the step 3, you just transform this leftover inventory rate times your standard deviation, then you find the expected leftovers. So here now you can see we order 5,000 units, so your Q equals to 5,000 units. You also have a higher leftover inventory, expected leftover inventory. So after you find the expected leftover inventories, and then you can also find expected sales, expected lost sales, and then you can also calculate expected profit based on these key values. So we do not repeat this process again. So we have introduced the news window model. News window model is the simplest inventory model. Is also the most popularly used in real operations. So that's actually very it's worthwhile for you to look into this model. You'll get a good chance or opportunity to use them one day. So here we try to summarize this model. So the news window model can be applied to the settings in which there is a single order or production opportunity. So basically you have no chance to replenish your inventory. And demand is uncertain, and there is a too much or too little challenge. So you order too much or too little, they both actually make it a negative profit for your company. And then the firm must have a demand model that includes expected demand or uncertainty in that model. So this is a stochastic inventory model. and we talk about how to construct a demand model. The normal distribution is broadly used in practice. At the order quantity that maximizes expected profit, the probability that demand is less than the order quantity equals the critical ratio. So this actually is actually the traditional or the classic solution for your news window problem. So try to maximize try to balance the underage and overage costs, and then in order to maximize the profit. So we have talked about a lot, but the key points in this lecture is you are able to calculate all this or evaluate your news window decisions based on the different performance measures. So there are two discussion questions. So the first question, if you order quantity maximize expected profit, then you actually means your Q star equals to the inverse of your normal distribution function regarding your critical ratio, and then that means your in-stock probability actually is the FQ star. So this FQ star equals to CU over CO plus CU. So that means the critical ratio is the in-stock probability. If your forecast uncertainty increases, so basically that means the sigma standard deviation increases. Do you order more or do you order less? So for example, you do the maximization for your if we continue to use profit maximization order quantity as an example, so if you remember, Q star actually equals to mu plus Z star times your sigma. So the sigma increases and your zeta value will be based on the standard normal distribution. So this critical ratio will not change. So that means your zeta value will be the same. So if sigma increases, that means your Q star or the quantity will also increases. And you can also put this in the other situations, for example, in-stock probability or others. So next, try the exercise, and then you will understand this entire model and the performance measures in a better way.